Well, we're going to look at number 16 in section 3.9. We're told to evaluate the derivative using logarithmic differentiation. That's what one of the section 3.9 talks about. And that's a particular method of differentiating. Here's the function we're going to differentiate. Now, you could differentiate this without logarithmic differentiation, but you would need to use what? You'd have a quotient, so you have to use the quotient rule. Up top, you have x times the quantity x plus 1 cubed. You've got to use the product rule. Down below, when you take the derivative of the bottom function, you've got a composition 4x minus 1 inside the squaring function. You got a chain rule. You got everything, and it's going to be a big mess in finding the derivative and then trying to simplify that down. Either way, the problem is difficult. Either way you look at it, but logarithmic differentiation is a way to make the actual derivative taking easier. In fact, when we use logarithmic differentiation, we will not have to use the quotient rule. We will not have to use the product rule. We have to use a little bit of a chain rule, but it's pretty easy. I'll show you down here in a minute what that is. Of course, we're going to use the properties of logarithms. I'm going to use the natural log, which is ln, log base e. And you should be familiar with these three properties of logarithms. The natural log of a product a times b is the sum of the logs. So keep in mind, remember why that's true. Logarithms are exponents. If you're multiplying like bases to different powers, what do you do with their exponents? You add them. So that's what this is saying in the exponents. What do you do with the exponents? When you're multiplying two bases, you add their exponents, and the individual exponents would be natural log of a, natural log of b. Okay, again, the exponents are the power on the base, in this case, which is e, needed to get a. That's what the natural log of a is. So in other words, e to the natural log of a would be equal to a. Okay, but that's the first property. The log of a product is the sum of the logs. The log of a quotient is the difference of logs, because remember, when you're dividing like bases to different powers, you subtract the exponents, right, to simplify. And then this is just repeated application of number one up here, the natural log of a to the n, which would be a times itself n times, right, would just be the natural log of a added up n times, or n times the natural log of a. We kind of think about it as, the power being brought down in front. It's an easy way to remember it, but that's what's happening there. Now, the other thing you need to do, we're going to use logarithms. First off, you need to, of course, know the derivative of the natural log of x is 1 over x. That's the derivative rule that we learned in this section, and we make use of it here. Also, if you have the derivative with respect to x of the natural log of u, where u is some function of x, that's a chain rule, right? And so you have to use the chain rule. The outer function is natural log of u. What's the derivative of natural log of u? That's 1 over u, just like we said up here. But then times what? Chain rule, derivative of the inner function, derivative of u with respect to x. Now, if u is just x, then this is just 1, and we would be up here. But if u is something else, then we're going to get that derivative. I could also write that 1 over u, du over dx can be written as a u prime, and I can bring this up top. And so often it's just written this way. In other words, the natural log, the derivative of natural log of u is just u prime over u, the derivative of u over u. And that'll be a helpful tool there for us as we're doing this. Okay. Well, let's go to the problem then. How do we start with logarithmic differentiation? Well, since these two expressions are equal, we're going to take the logarithm of both expressions. They must be equal. So the natural log of y is equal to the natural log of all this stuff. Just copied it. Okay, so now properties of logarithms come into play, right? We're going to, first of all, make use of property 2, log of a quotient. So I've got this quotient up here. The numerator of my quotient, the a here, is x times the quantity x plus 1 cubed. So I take the natural log of that thing minus the natural log of the bottom, right? That's making use of property 2. Okay. Now, if I look at this expression, natural log of x times x plus 1 cubed, I can make use of property 1, because there's my a and there's my b. I'm going to take the natural log of a times b, and that's the natural log of a plus the natural log of b. And of course, minus the natural log of this over here. So that was using property 1. And finally, I'll use property 3, which is going to basically get these exponents to come down, right? So the natural log of x plus 1 to the third power. So a is like x plus 1, and 3 is the n. We bring the n down, and I get 3 times the natural log of x plus 1. And then over here, I can bring the 2 down, 2 natural log of 4x minus 1. So I've used all three properties here to expand this out as much as possible. hopefully you remember doing this sort of exercise in pre-calculus where you were either expanding or going in the opposite direction, compressing logarithmic expressions. Those were tools that you learned, hopefully, in pre-calculus. That's what we're going to use it now. We did all that work. That's a lot of work, but we've made the derivative easier. And now I'm going to take the derivative. I want to know y prime or dy with respect, dy dx, y, the derivative of y with respect to x. So I'm going to just take the derivative with respect to x of both sides. Now, it's not a problem over here. Here, we just have to realize, since I have natural log of y, it's a chain rule, right? It's not the derivative with respect to y. It's the derivative with respect to x. So it's the same rule up here that I was talking about, where instead of u, I have y. It's going to be 1 over y, the derivative of the outer function, times the derivative of the inner function y prime. Right? Chain rule is what we really have here. And again, we're looking for y prime, so it's a good thing that here it is. We just have to solve for it here in a second. Now, over here, we take the derivative. What's the derivative of natural log of x? As we said above, that's just 1 over x. What's the derivative of 3 times the natural log of x plus 1? Well, we got a little chain rule. 3 is a constant multiple. And remember what I said, it's just the derivative of natural log of u is u prime over u. Well, u here, in this case, is x plus 1. All right, so u is down here. What's u prime? What's the derivative of x plus 1? It's just 1. So this is just 1 over x plus 1. Here I have minus 2. 2 is a constant multiple. And here my u is now 4x minus 1. So this will be u prime. Well, what's the derivative of 4x minus 1? That's 4 over u, right? U prime over u. So again, it's chain rule each time. Simple chain rule, okay? Now, all I have to do is solve for y prime. How do I do that? Well, I want to multiply by y, multiply both sides by y. So y prime is y. Put in all this stuff in parentheses and clean it up a little bit. 3 times 1 over x plus 1 is just 3 divided by x plus 1. 2 times 4 is 8. And we're there. Now, can I express my derivative in terms of x only because this is y here? Yes, we can, because remember, the original problem told us what y was. Y was all this stuff. So I'm going to just take that whole thing and replace y with it. And here is the derivative in terms of x. Now, for me, on a test, you know, this is fine. I would say stop here because you've got the derivative as a function of x. Sometimes Achieve's a little finicky. I've been trying to get them to accept this answer. If not, let me show you how to simplify it and write it maybe in a little bit better form. But we have a lot more work to do. Kind of. And in some sense, makes all the work that we did kind of, not worth it maybe. But it's not really too bad. It is a bit of algebra. I want to just look at combining these 3 fractions is all I'm going to do, and then see if I can, find any factors in the numerator and denominator to cancel. So notice the least common denominator. I've got an x, an x plus 1, and a 4x minus 1. So the least common denominator is just the product of those. Okay, and so again, I got this expression out here, and then in brackets I've got 1 over x. I want to write that over that common denominator, so I need to multiply top and bottom by x plus 1 times 4x minus 1. And when I do that, I get x plus 1 over x plus 1, 4x minus 1 over 4x minus 1, right? I still have this x down here, so just multiplying this equivalent fraction, right? Here I have x plus 1, so I need to multiply top and bottom by x times 4x minus 1. And I've got a 3 up there, so I've got 3x times 4x minus 1. There's my common denominator. And then here I've got a 4x minus 1. I need to multiply top and bottom by x times x plus 1. So 8x times x plus 1. And that gives me the same denominator. Notice that's plus and that's minus. Okay. And now I can do some work, okay? I have the same denominator for all of these. Let me FOIL this out. I get first is x times 4x, 4x squared. The outer is negative x, inner is 4x. That gives me a total of 3x. 1 times negative 1 is negative 1. Over here, I distribute the 3x. 3x times 4x is 12x squared. 3x times negative 1 minus 3x. Be careful here. It's negative 8x times x. That's negative 8x squared. Negative 8x times 1 is negative 8x. Now we just combine like terms up top. 4x squared plus 12x squared is 16x squared minus 8x squared. That gives me 8x squared. So I've combined all my x squared terms. My x terms, 3x minus 3x, that's 0x. Minus 8x is minus 8x. And then I just have a negative 1. Okay, so I just simplify by combining like terms. Now notice my denominator is factored, and now in this form, do you see some common factors? Because this is really, just this fraction times this fraction. Notice these common factors in the numerator and denominator. I've got an x here and an x here. I can divide top and bottom by x. And I've got an x plus 1 factor in the numerator and denominator. I can divide x plus 1 here. That's going to leave, what, 2 of these x plus 1s. Okay, and so finally, I've got x plus 1 squared, and then just times this stuff, 8x squared minus 8x minus 1. Can't really factor that any further. Okay, so I'm going to leave that there. And then 4x minus 1 squared times 4x minus 1 in the denominator is a total of what? Add the exponents, 4x minus 1 cubed. So this is, I think, what Achieve is wanting. It is a nicer form maybe than the original answer. They are equivalent. Okay. Bottom line is the derivative of this function is just nasty. It's just a lot of stuff going on, but you can see where the logarithmic differentiation helps us so that we don't have to use quotient rule, which is bad, and then product rule. Okay. All right. I hope this is helpful. This was a long one, a lot going on with this one, but that's a good example of logarithmic differentiation. Probably the hardest one you would ever have to do. Okay. Hope this is helpful.